I make all these video solution. Who's it for? This is rearrange array to maximize prefix score. Okay. So you are given a 0 index integer array nums. Are they ever not 0 indexed? You can rearrange the elements of nums. Well, you can rearrange the element of nums to any order, including the given order. Okay, so you can take these numbers in the list and you can swap them out. You can move some over here, move some over here. Do whatever you please. And you can also decide that you don't want to change them. So you can just leave them in the order that they're given. Let prefix be the array containing the prefix sums of nums after rearranging it. I'm pretty sure if you're approaching a recently released competition problem of the medium classification, you probably know what a prefix sum is, but nonetheless, prefix I is the sum of the elements from 0 to I in nums after rearranging it. Okay, so you can take the system of nums, you can rearrange the numbers, and then you calculate this prefix sum, which is essentially just a running sum through the system. The score of nums is the number of positive integers in the array prefix. Okay, so we look at each indice of this prefix sum, and the number that are positive corresponds to our score. Return the maximum score you can achieve. So the idea is we take our initial nums that's given, for example, this, right? So we have nums equaling 2, -1, 0, 1, -3, 3, -3, all right? So we're given nums like this. Now, if we were to not change this system at all, what would the prefix sum look like? Well, the prefix sum is just a running sum of the system starting from -0. So you start by summing up 2, right? And in the next system, you do 2 plus -1, great, because you're counting from the beginning. The next one, you do 2 plus -1 plus 0. So 2 plus -1 plus 0. And the next one, you do 2 plus -1 plus 0 plus 1. So 2 plus -1 plus 0 plus 1, and then 2 plus -1 plus 0 plus 1 plus -3, and then 2 plus -1 plus 0, plus 1 plus -3 plus 3, and then finally 2 plus -1 plus 0 plus 1 plus -3 plus 3 plus -3. And then the sum of that, of course, is the value of the prefix sum. So this has value 2. This has value 1, this has value 1, this has value 2, this has value -1, this has value 2, this has value -1. And then if we looked at these, the score, right, is the number of prefix sums that equal, that are positive. So only this one and this one don't meet the condition, while this prefix sum is positive, 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 positive. And then also a side note, it might not be super important for this problem, but you'll notice that I was able to calculate these sums quickly. Why? Well, if I already calculate this sum, then I can use what I know it is to calculate the next sum, right? So I don't need to recount everything. I don't need to go through this whole system again to calculate this. I can just take the calculation from the previous system, right, up to here, because I know this is 2, then I can replace all of this with just 2, and then add in the -3, right? So that's the idea of prefix sums. You can use the previous sum to find the current sum by just adding in one additional value, right? I can use all of this from the previous sum, add in one additional sum to get this, so 2 plus -3, 1 plus -1 plus 3 to get 2, and then 2 plus -3 to get -1 at the end. So that's the idea of using prefix sum. So using this approach alone, we get 1, 2, 3, 4, 5 solutions. But it turns out if we were to intelligently rearrange the system, we could get 6 positive systems. So why is that the case? Well, it kind of seems here, right, the solution is greedy, right? Because, like, we're just trying to maximize the total number of sums that are positive. So if you were thinking about this intuitively in terms of something you understand, right, if you want something, you're basically trying to keep your sum positive as long as possible, right? So what you should do is try to maximize your sum and then make it small as slow as possible, right? Meaning that, like, I want to take my sum and I want to maximize it so it's as positive as possible. So then when I start adding negative numbers in, it stays positive as long as possible, right? So in order to make this as positive as long as possible, since that will maximize my score because I'll have as many as possible positive sums, I should try to maximize the current running sum and then make it small, as slow as possible. So to maximize my running sum, what I'll do to nums is I'll maximize the values as I add in the running sum, right? So what I'll do, now I'll put this here so it's not covered by my face. So in order to maximize my sum, well then I'll first add in 3 because 3 is the maximum number. All right, so that'll maximize my sum. I'll keep trying to maximize my sum. I'll add in 2. And then I'll add in 1. And then I'll add in 0. Right, so that'll maximize my sum. But now that my sum is maximized, I want to minimize it as slow as possible because I want to keep it positive, right? Like imagine it's like, I want to keep, like, imagine this is money that you collect or you spend. If you want to keep your balance positive as long as possible, you should collect all the money up front, right? You should get all your money as high as possible up front and then remove the littlest amount of money every single day, right? So instead of removing -3 the next day, I'll remove -1 the next day. That way I'm removing the minimum amount of money. So I'm trying to keep this ship afloat as long as possible. So to keep it afloat as long as possible, I want to front collect all the money to make my balance as high as possible and then spend the least amount of money every day to keep me from going negative, right? Because the thing you don't want to happen here is that it's positive, and it goes negative, then becomes positive again, because you very likely could have made it positive, and stay positive the whole time, right? The idea is you don't want this situation here, right? This becomes -1. Well, if you had just added the 3 before you subtracted this -3, it would have stayed positive, right? So you might as well front load all the positive values. And there's probably a formal proof, right? There's probably a formal proof where you could say that the best idea is to front load and then you would do some sort of proof by contradiction. I'm not going to do that. I think it's pretty intuitive what we're doing here, right? So I remove the -1. And then finally, the only choices I have now are to remove the -3 and the -3, right? So I'm trying to keep my account afloat. I'm trying to keep my account positive as long as possible by essentially front loading as much deposits, I guess, as possible, and then unloading or withdrawing money as slow as possible by withdrawing the smallest amount of money that I can possibly. And then you'll notice, well, what is this array? Well, this array is essentially sorting the source array in descending order. So then what we can do is we'll just do a running sum in this system. So I'll have a prefix sum here, which initials value is 3, so that'll give us a solution. And then the next value is 5, because I add 2 to the previous 3, and that's a valid solution. The next value is 1, we get 6, and that's a valid solution. And then we have 6 again, which is a valid solution. Now we start losing money, but since we front loaded as much as possible, we can try to keep it positive as long as possible. So this is 5, so even though we spent money, we're still positive. This is 2, right? I'm just doing a running sum again, so I'm just taking whatever the previous sum was and then adding in the current value. This is just a contracted version of this system here. It's positive. And then finally at the end we go negative, but since we try to front load it as much as possible, we don't need to worry about that. So in the end we have 1, 2, 3, 4, 5, 6 solutions. So in order to do this, it's pretty simple, right? We'll just keep a prefix sum, which is our running sum, and then we'll look at each index and number in enumerate. We'll sort the list. We'll sort the list, and the way that we'll sort it is in descending order. So it's basically just reversed, but we'll do it like this. So we'll take the negative, we'll take the num, and then the negative the num to sort it. Now the idea is why am I doing this enumerate? Well, as soon as your solution becomes negative, it's going to stay negative because it's sorted, right? So as soon as you encounter a number that makes your prefix negative, all subsequent numbers are negative. So all subsequent solutions are invalid. So you can kind of end early in many cases, right? Like if you had the example where you had 3, -4, -4, -4, -4, right? As soon as I count this 3, I have one solution, then it's -1. When it's -1, since it's sorted, the subsequent numbers coming after this are going to still be negative. So I can just end early. I'm like, okay, I'm negative now. The way I set up my bank account is that I front loaded all the positive transactions. And that means if I'm negative now and I just encountered, if I'm negative now, I'm never going to be positive again, right? Because if I'm negative, that means that I'm starting to process negative transactions. The game's over right at this point, because I've done everything I can to maximize my account. I've done everything I can to minimize the money that I take out. So at this point, if it's negative, it's going to stay negative forever. So we'll kind of look at that idea here. So what we'll do is we'll take the prefix and we'll add in the current number that we're dealing with. And then we'll ask the question, well, if the prefix is negative or less than or equal to 0, right? Because we want to know the total number of positive integers. If it's less than or equal to 0, it's never going to be greater than 0 again. So we'll just return whatever index we're at, because the index we're at will correspond to the what? The index we're at will correspond to the total number of solutions that we looked at, right? Because for an index 1 and it fails, that means index 0 worked. And then if we get to the end, that means that we got the whole system to work. Is that -1 or I think it's +1? Now, this index idea is confusing. You could just keep a count, right, of the total solutions that work, and then return the count, add 1 to the count every time you do it, but it's a bit more concise. All right, boom, son. Doesn't get much better than that. So what is the runtime and the space complexity of this solution? Okay, so let's say n is the length of nums. So for time, we have to sort nums. We'll do an in-place sort, like heap sort or heap sort, in-place heap sort. And we have to look at every number, and we have to sort the nums first. So we look at all n nums, but before we look at all n nums, we sort it. So that takes n log n time. So n log n plus n, it's going to get overshadowed by n log n. So that's n log n time. And then for space, well, if we believe that this is going to sort it in place, so we take nums and we sort it in place. Now, this might not do that, but in theory, you could do that. So let's just assume for this example that sorting it this way does do it in place. If it doesn't, then we can look online. What is a Python sorting algorithm sorting in place? And it might make the solution a little bit more ugly, but I think it's enough to just say that this could happen in place. So let's say that this is in place sort. And the reason why we're doing that is because, okay, so sorting doesn't take n log n space. It takes constant space. And then we just have one variable. So regardless the size of n, we're just going to scale this prefix variable with that num. So in terms of space, that's O of 1. Right? We're not going to be updating any array. We're not going to create anything else besides this prefix thing that we're using to sum. Okay. That's it, guys, for today's video. Hopefully that makes a little bit of sense. It's kind of one of those greedy approach problems you have to think about intuitively or you're not going to get the answer. Peace out.